For the final lecture this week, I wanted to take the time to live code some data exploration in pandas for you. And we're going to be working today with a data set that we'll probably come back to in the future. But for now, we're just going to download it and start exploring it. So I'm going to open a new notebook, which I'll call Titanic. And we're going to go to the data science competition website called kaggle.com. So I believe I mentioned this website in an office hour, but Kaggle is a website where that hosts data science competitions. So if you click the competitions tag, you can see there's all kinds of companies that pose problems for data scientists to work on. And these can be things like this company TGS, a geoscience data company, is interested in finding large salt deposits on the world, presumably to mine. And they furnish you with a data set. So this is a data set of images from various locations. They're each 101 by 101 pixels, classified as either salt or sediment. So the idea here is to train some kind of model that can look at these images and correctly classify the image as either showing salt or sediment. And they have a nice description of the background of the problem. And Kaggle's a really useful tool for practicing your data science skills because it presents you with a well-defined problem. They give you the data to work with. It's often, not always, but it's often cleaned data. Sometimes you'll have to do your own data cleaning. Furthermore, often there are data scientists making their work available for you to build on or think about. So they have kernels, which are basically Jupyter notebooks. So here is one competitor's approach to the problem, in which they explain their approach, and they have the code which you can run. There's additionally a discussion board, and people leave comments as well discussing this particular approach. So this site's a pretty good resource for kind of practicing your skills in data science. You're given a well-defined problem, you're given a data set, and there's a community that you can tap for advice and discussion. Now, most of the, if not all of the competitions on Kaggle, you will need to make use of machine learning, which we have not discussed yet. We are still at the stage of just learning how to wrangle data, how to, read it into Python and get it in a format where we can easily work with it. And that part is, kind of universal for data science problems. Not every data science problem is going to require that you use machine learning, but all of them will require you to do some amount of data wrangling. So today we're going to practice that by having a look at their Titanic competition or challenge. They have several challenges that are labeled Getting Started that are meant to acquaint you with the Kaggle platform and how to participate in competitions. So if you go to the Titanic competition, you can download the data by clicking on the data tab, and we'll just download the training data for now. Let's see here. I have to sign in order to do this. So you may need to create an account with Kaggle in order to use their data. But once you've signed in, you should be able to download the training data. So now that's downloaded to my local computer, and I'll just upload that into the data directory of the Python DS directory, and I'll call that Titanic. And now we'll load that file into pandas and do some exploration, and by doing that we'll explore some of the functionality of pandas. I've given an overview, a high-level explanation of how to work with pandas, and we've done a few examples, but I find that often students don't have students need a lot of practice with the concepts before they really understand what's going on with group bys and joins and those kinds of things. So we'll import pandas, and we'll read the data into a data frame. And the data is nicely formatted. We've got a header that gives us all the column names, and there was no issue with like the delimiter or anything like that. Maybe what I should have done first was look at what's in the file. I've worked with this file before, so I already knew, but I would have seen there's the header, there's these, it's separated by commas. One thing I maybe should have worried about, but Pandas already was smart about, was we have a string in here that contains a comma, but since the string is in quotes, this comma is ignored as a separator or delimiter, and instead is interpreted as part of the string. So Pandas was smart about that. There's also some missing data. But again, I don't have to worry. It just shows up as a missing value in that column. So now I've read in the data. That part was fairly easy. And now we'll want to explore the data and get a feeling for the relationships in the data and the distributions of the various variables. So, for example, I see there's people who survived and people who did not survive. Obviously, when the Titanic sank, many people perished, but some of the passengers survived. So the first thing I might want to do is just see how many people survived and how many perished. Now, what I want to do then is count how many zeros there are and how many ones there are. And there's a number of different ways I could do this. If I wanted the number of ones, I could just take a sum of the survived column. And if I wanted the number of zeros, I could say take 1 minus the survived column and take the sum of that. And in fact, there's 891 passengers in all, and we see that these two numbers sum up to 891. Another thing I could do is to group the data frame by who survived and who did not. And then I could take some column, it doesn't matter which, and just perform a count. So 342 people survived, 549 perished. And perhaps the easiest way is often we'll want to group up the data frame by some field and then simply count how many elements there are in each group. That's a very common thing to want to do. In which case, we can use the value counts method. So if we have a pandas series, we can group up that series by the values and count how many elements there are in each group. Notice that these give slightly different results. So here we had a pandas series that we kind of grouped by its own values, and we counted the number of elements in that group. So this returned a pandas series called survived, where the index are the values of survived, and then the values are the counts. Here we grouped the data frame by survived, and then pulled out the passenger ID series. So the name of the resulting series is passenger ID, and then the name of the index is survived. So we get slightly different objects out from these two methods. But for the most part, the part that we care about is the same. The index and the values are the same. So this is kind of starting with a very crude method, sort of a numerical method, and then building up sophistication, where we get a single object as output and are treating those who survived and those who did not as different groups. And we could likewise do this for, the class of each passenger or the sex of each passenger. But, this gives us a nice view of the distribution when there are only a couple of categories But it's not as useful for things like age or these variables, which are how many siblings or spouses the passenger was traveling with, and how many parents and children the passenger was traveling with. So for example, let's create a new column called party, or party size, that will be the sum of the number of siblings, spouses, parents, and children that a passenger was traveling with. And if we look at the distribution of party sizes, this is a little bit too many. This is too many categories, or too many groups to really easily be able to understand at a glance. You know, I can see most travelers were traveling alone. Quite a few were traveling in, with one or two companions, and then far fewer were traveling with more than two. But that's sort of like a gross. What I'm doing is I'm looking at this and I'm actually reducing the amount of information further with my power of inspection. I'm saying like, okay, well, there's like kind of three groups that I can like break out here. So because I can't look at these 8 or 9 numbers and make sense of them all at the same time, I actually need to reduce them further mentally before I feel like I have a grasp of what's going on here. So, of course, one great alternative for dealing with this sort of a situation is, instead of creating some kind of chart with a bunch of numbers, is to create a histogram. And now I can easily see essentially what's going on is there's almost like an exponential decay in the number of passengers traveling with ever increasing party sizes. So this gives me a lot more information at just a glance. Not only can I see the dominance of people who are traveling alone and the prevalence of people who are traveling with just 1 or 2 companions, but I can see clearly this kind of exponentially decaying trend that holds out over the entire range of data. And if I wanted, I could even try plotting something like, we'll say x equals df party size max np dot a range. And we could try plotting a curve what shall we call this? So we'll have, say, 500 times an exponential decay of, let's just do minus x for now, or 1 times x. numpy not defined. So, here we see I've plotted a possible kind of like exponential decay law or fit for the data. And I've just been guessing the parameters. I haven't actually performed any kind of fit, but what I'm trying to accomplish is to visually illustrate the pattern that my eye was able to seize upon when I created this plot. I looked at this plot and I said, oh, there's something like exponential decay going on here. And I'm just putting a curve on top to illustrate that trend. It does really look like exponential decay. And in fact, given that that is true, we could even try np.log df party size dot this range. There we go. Do I want the log? What do I want here? So, okay, that's not actually the transformation I want. I want a different transformation, but it's a little bit of extra work and it doesn't give me that much more insight. So, yeah, all I'm trying to do here is explain that when I look at these numbers, I don't think exponential decay. I just, at most, can say like, okay, a lot of people travel alone, quite a few people travel with like one or two companions, and then there's less people traveling in larger groups. Here, I look at this and I immediately think exponential decay. So, as I mentioned in a previous lecture, visualization, incredibly important for exploring data. Now let's consider age. So age has a similar issue. I can't just count the number of passengers at each age and really have any understanding of what's going on. Ages come in all these different quantities, even completely ridiculous quantities like 0.92 years old or 14 and a half. There's 88 ages here. So and it's immediately more natural to plot a histogram, which gives us an idea of the age distribution. It peaks around 20 or 30. There's a substantial amount of young children, and especially infants, and then kind of a decay off towards older ages. Another thing is we could, of course, use the describe method to get an idea of the summary statistics. So out of 714 passengers that actually had age information, not everyone did, the mean age is about 30. That is visible in this plot as well. This is where the peak is, and if I kind of like was searching for the center of gravity in this plot, I would estimate it's around here. Standard deviation is 14, so on either side, the plot falls off about half of its height over a range of about 15 years. So 30 to 45, 30 down to 15, if I were drawing a smooth curve on either side. 25th percentile, median, 75th percentile. So we can see there's a huge gap between the 75th percentile and the max, a much smaller one between the 25th percentile and the min. So this tells us the graph is heavily skewed to the right, which it is. Again, we can see that from the histogram. But we can also interpret it from these numbers. And this is all well and good, but so far all I've been doing is analyzing these different bits of information in isolation from each other. What if I actually want to analyze these things together? Oh, one more thing I want to show. Sorry. So I have a few percentile cuts here, but if I wanted more percentile cuts, I could use Panda's QCut function. So I could say that I would like the 10th, 20th, 30th, 40th, and so on percentiles. And then I would get the boundaries for the percentiles and which percentile each passenger belongs to. And if I were to do value counts on this and sort the index, I have a number of bins of my choosing of given the sizes. So I've actually constructed a histogram here where each bin contains 10% roughly of the data. There's clearly variations in that, but it's roughly 10% for each one. Okay, so if I want to analyze variables together, then there's a number of ways I can do that. I can do it visually, which we'll have a look at first, or well, we'll have a look at that actually second because it doesn't involve pandas and I want the emphasis here to be on working with pandas. But I can also do it analytically, numerically. So, for instance, I might be interested in the distribution of ages among passengers who survived versus those who did not survive. So I might want to look at, for instance, the mean age based on who survived and who did not. So I'll group up my passengers by who survived, look at the age column, and ask for the mean age. And we see here that people who survived seem to be slightly younger than those who did not. But is this significant at all? It's hard to say. The difference looks to be somewhat kind of small. You know, the distance between 28 and 30 in this histogram is actually within one bin, and there's a broad peak in ages of our passengers there. So quite a few passengers fall into this age range. So the difference between 28 and 30 is not so big necessarily. What if instead we looked at the reverse? Based on what age someone is, did they survive? or what proportion, so mean of a variable that's 0 or 1 will give us the proportion of people who survived. So what proportion of people survived grouped by their ages? Well, remember, there's a lot of different ages, so we're going to have a ton of different groups. So this is not going to be a useful approach, unless we group our data frame instead by some bins of ages. So we'll bin our ages into some groups. So we'll say 0 to, hold on, let me look up really quick the format for how this should work. Bins. Sequence of scalars to find bin edges for non-uniform width. Great, that's what I want to do. So we'll do, say, 0 to 5 for very young children, up to, say, 18 for adolescent children, or children who are not infants but are still not adults, up to, say, 25, 35, 45, 55, 65, 85. So these are not uniformly sized, but I've made cuts where I expect maybe there are qualitative differences between types of people. Very young children, like, babies. Children, but not babies. Young adults. More established adults, kind of on into middle age. And then the elderly. And now we see something more striking, which is the elderly were very unlikely to survive. A very low proportion of elderly people survived. Now, this might not have been cruelty. This could just be, when the Titanic sank, everyone was out in freezing cold temperatures. And the elderly may have been more susceptible to the elements than young people. On the other hand, infants or babies were very likely to survive compared to other groups. So this tells us more about how likely people were to survive based on how old they were. So for adults, even if you were a child up to a young adult, your likelihood of surviving was as good as any adult. If you were a baby, you were substantially more likely to survive. If you were elderly, you were substantially more likely to perish, to die. So this shows also we don't need to group our data frame strictly by things that are in the data frame. What I did here was construct a pandas series. But since the index of that series is shared with the data frame, pandas is still able to use the values in this series to construct groups of indices, and thereby group this data frame by which indices belong to which group in this series. Let's do some more somewhat advanced things, or more creative things. So we have a bunch of names here. And it might be interesting to try and extract some information from them about who might survive and who might not survive. So for example, we have Miss and Mrs. Presumably people whose names begin with Mrs. are married, while those who begin with Miss are not. Were married women more likely to survive than unmarried women? Let's try to find out. So if we look at the names, we can ask for those rows where the names contain either Miss, Miss, or Mrs. So these pipes count as or in what's called a regular expression. So I'm doing what's called pattern matching using regular expressions. So strings that contain Miss or MS or MRS. And then what I'll want to do is try to extract the title. So that's going to be another string operation. And we notice all the names have their last name, comma, then their title. So what I can do is split on comma space. So after I did the filtering, I have to look at the name column. And now I've turned these strings into lists where the first element is the last name and the second element or remaining elements are everything else. And if I apply a lambda function where I return the second element of these lists, I again just have these strings. And now the titles appear to all end in period space. So I'll apply another string operation for period space. And now I'll extract the first element of these lists, which contain the title. So now I've got all my titles. But we've got a lot of stuff chained together here. This is really hard to read. So let's rewrite this slightly to be easier to read. So first, I'll actually titled women. So women with titles. So I'll first just look at the filtered data frame here. Of course, I could have filtered this in an entirely different way. I could have done df sex equals female. And this would have also given me all the women. Perhaps a bit easier. But I wanted to show this string operation. And then I'm going to take the titled women. I'm going to look at their names. And I'm going to want to apply a function that we'll call extract title, which we haven't defined yet. So I'm going to come up here and we'll define that. Extract title. And the thing we're going to get is a name. So what should we do with this name? Well, a name is a string. And the thing we want to do is essentially what we're doing here. But instead of acting on a series using this pandas string operations, the thing we're acting on is a string. So we'll use the Python string operations and indexing, which looks very similar, but we can see is slightly different. And now we have the exact same functionality, but it's somewhat easier to read. So now we have all these titles. And if we take titled women and we group by women's titles, we can take survived and look at the mean, the proportion of who survived. So 100% of people titled lady, or I guess this is mademoiselle, or MS survived. And it's probably because, what if we do, instead of here a mean, we do an ag, and we have a mean but also a count. And we see each of these cases have exactly one passenger who happened to survive. So those three cases are not so interesting because they correspond with just one passenger. What's more interesting is to look at Mrs. versus Miss, which have over 100 passengers each. And we see Mrs. had a survival rate 10% higher than Miss. So being a married woman perhaps improved your chances of surviving compared to being an unmarried woman. And we can think of all the kinds of reasons this might be the case. Perhaps being married correlated with being higher class, or it correlated with having children or young babies. And we already know that young children or babies were extremely likely to survive. So perhaps their mothers were also likely to survive. In fact, one way to perhaps check that would be to look at not only women with the title Mrs., but who also were traveling with, who had a parent-child count of 1. So, unmarried women okay, so let's consider the married women. So married women who had, so we have whether or not that person was traveling with a parent or child or was by themselves. So married women who had no parents or children with them, parent-child was not greater than 0, were actually even more likely to survive than those who did have parents or children with them. So actually that intuition, that maybe the mothers of young children were more likely to survive, appears to be wrong, because married women who were perhaps traveling with children were, it was more likely they survived, 85% survival rate, when they had 0 parents or children with them, meaning 0 children. In fact, in both cases, for married and unmarried women, it appeared that you were more likely to survive if you weren't traveling with a parent or child. So that's rather remarkable, I think. Just going to check the time here. 45 minutes. Okay, good. Another thing we could look at is, I mentioned maybe married women tend to be higher class. So we could also group this by titled women, P class. And why don't we go ahead and, I want to get rid of these rows that have lady, MLE, and MS, because they're just cluttering up the results and making them hard to look at. So let's drop titled women where, or rather, women's titles is in lady, MLLE, or miss. And here I won't drop these. I'll actually use this as a filter. So again, this is getting pretty long and complicated. Difficult to look at. So it may be a good idea to introduce some more intermediate steps, either by having the results of this filter be stored in some variable. Unfortunately, there's not a lot we can do here to make things like the group by shorter or anything like that. But what we see as a result here is the proportions appear to be the same for Miss and Mrs. based on class. So if you were unmarried and first class, you had a 95% survival rate. Second class, 94% survival rate. Similarly, for married women, first and second class had survival rates in the 90%. It was third class that had a significant death rate. But what differs is the distribution of married women and unmarried women across these classes. Married women were evenly distributed across the 3 classes, whereas unmarried women were much more likely to be lower class. About half of the unmarried women were lower class, whereas only a third of the married women were. So the reason for the survival rate difference between unmarried and married women doesn't appear to have to do with whether they're mothers or whether just they had husbands who helped them get space on lifeboats or anything like that. It appears like it's just perhaps driven by class. And then it's explained by the difference in distributions of women across the classes based on whether they're married or unmarried. So this is pretty interesting. We've discovered that married and unmarried women appear to have different survival rates. But the difference is not driven by whether they're married or unmarried. It's driven by what class they belong to. And it's simply that unmarried women are more likely to be lower class. What other kinds of analyses can we do? So we already have, this class variable. But imagine we didn't for a moment. Because in some data sets, maybe we won't have something like that. We could perhaps derive this class variable from the fair data. So let's look at the fairs, the distribution of fairs. So clearly there's, it's heavily skewed. A great deal of fairs appear to be between 0 and maybe 20. I don't know what units this is in, maybe British pounds. There's a step here between maybe like 40 and 80, and then more expensive than that. So if we looked at, for instance, the summary statistics for the fair, the mean fair was 32. Standard deviation was quite broad. The median was 14. So this discrepancy between the mean and the median tells us, the distribution was heavily skewed. And then, again, we see this heavy skewing. 25% sits between 0 and 7. Another 25% sits between 7 and 14. Another 25% sits between 14 and 31, a width that is twice as large as the previous two quartiles. And then the last quartile goes all the way out to 500. So maybe we'll segment this into 3 groups. Say 0 to 15. To looking at this, I'm going to go up to about 80, and then we'll do 600. Which is greater than the max, or 515, whatever, it doesn't matter. Something greater than the max. And I believe, let's see here, pandas cut. Bins, labels. So I can also specify what labels to return for each bin instead of these 0 to 15, 15 to 80, etc. So we'll say labels equals 3, 2, and 1. And we'll call this So, just as an exercise, it might be interesting to see how well we actually classified people in P class versus fair class. So what I want here is a confusion matrix, it's called. Oh, this is scikit-learn. I don't want that. Maybe I can just do df fair class p class core. Okay, I don't know why this isn't doing what I want. Well, very simply, we can calculate accuracy anyway by looking at how many we got right. So if we got it right, we'll have a true, otherwise we'll have a false. And the proportion of trues was close to 60%. Not bad. Better than random guessing, for sure, because randomly guessing would give us 1/3, roughly. So we can construct this fair class field if we had to derive this kind of like class variable. But I'm going to do it in a slightly different way. So this is sort of like the intelligent way that I've shown thus far, but I'm going to do it in a slightly different way, but to illustrate a workflow that is fairly common. So say I just said, when I say something was oh, that's not going to work. Sorry, I have a particular thing in mind. I'm trying to come up with an example. So this is contrived, and I apologize, but I can't think of a better way to do this. So say we had a reason to think your class status was related to your fare, but also to your age. And so people in different age groups, you know, if you paid below the median fare for your age group,
you were maybe lower class. If you paid above the median fare for your age group, you were upper class. So then we would need to know the median fare, but for each age group. So we have median fares for each age group. And now we want to make a fare class where we ask, is the fare greater than the median appropriate for a given row's age group? But we need to know which age group. This is not going to work, basically, is what I'm trying to say. We need a way to compare the fare in this column to the appropriate median. These two things have different series, so we can't compare them because the series have different indexes. You can only compare identically labeled series objects. The issue is I have all these fares. For this passenger, which of these median fares am I comparing this 7.25 to? So rather, we need to find a way to match up the two series. Now we can imagine this doing a couple different ways. We could say set the index of the data frame to be the age group, and then we have a fare indexed by age group. Can we compare these? Not quite. Because even though these have the same values for the indices, the index here only has, 7 or so elements, while the index here has an element for each passenger. There is, I believe, greater than pandas. Okay, this didn't work as I expected. So what we can do is we could construct a age bin field in the data frame. Then, so now this will be group by DF, or just group by age bin. And then, if we want the fair to construct a fair class, we could take df fair and apply lambda x, just the number, the fair, whether that is greater than the actually, I'm going to do it this way. So we want to check, so x here is actually going to be a row. So we want to check if that row's fair is greater than the median fair for the age bin of this row. So we can remember this group by with the median returns this series. We can slice this series using the row's age bin. Fair occurred at index passenger ID. I need an axis equals 1. Nan occurred at index 5. If row age bin else no. Now okay, so I didn't accomplish this quite in the way that I wanted to. But what I was ultimately trying to show, and didn't really explain very well, is we have this aggregation. For some groups in our data. And we wanted to use this aggregation to do a comparison with each row in our original data frame. So we needed to somehow join, essentially, or do a lookup or something like that, appropriate to each row in this aggregate. But there's way fewer elements in this aggregate than the original table. So how do we join them together? Well, we could do something like a merge. Cannot merge data frame with series to frame. So here we have we use a merge to where we use the index of this series matched against the age bin column of the data frame. That's one way to get this the correct median value into the original data frame. And then we could compare the age median against the fair. But we can also apply a function where we calculate the appropriate median for the age bin that we are currently looking at. So we filter the data frame to that row's age bin and then calculate the median fair. And that will give us a single number for the correct age group. So there's many ways to get around this, but whenever we are trying to compare an aggregate to a table, we're going to have to devote some thought to planning how we're going to put the elements of the aggregate in correspondence with the whole of the table. We'll need to come up with some kind of mapping. So hopefully that wasn't too unclear, and I highly encourage you to download this Titanic dataset, try and follow along with the video, and come up with your own experiments and explore the data, particularly what kind of factors were likely to contribute to someone surviving or not the Titanic disaster. All right, so that concludes the lectures for this week. Next week, we will be discussing SQL, which will also be in the tabular data structure kind of format. And I believe that's probably it for next week. We will probably be only discussing SQL.